Swayam Prabha. Digital India. Educated India.
So here is what simplifying reductions does. Okay. Normally, when you are working on a compiler, the human has a problem to solve. They come up with an algorithm to solve the problem. Then they write a program, and an optimizing compiler improves the program. Okay. And by that, a program can give you, the compiler can give you at best a constant factor improvement instead of something that is taking the asymptotic complexity of your program remains the same. Okay. So simplifying reductions is a transformation that invents algorithm. So it is a compiler technology by which the compiler can invent an algorithm. So that's why we had this paper on it about 15 years ago, and it has got some very recent interest because there are many algorithms. Well, I'm getting a little bit ahead of myself. Okay. So if you have a compiler that can take a program that is cubic complexity and execute it in quadratic, then you have basically unbounded speed up because you have improved the asymptotic complexity. Okay. All right. So can I take a quick look and see how we're doing? We have about 10 minutes, right? Today? Hello? I'm going to show you some pictures today in 10 minutes, and then I'm going to ask you to go back, and by the end of the day, in the evening today, I will talk about the continuation of this. So right now, I just wanted to give you a sneak preview of simplifying reductions. Okay. So what is a reduction? A reduction is an associative and commutative operator. It doesn't have to be commutative, but in the examples that we are looking at, they almost always happen to be commutative. It's not a requirement. It is but it has to be an associative operator. It is applied to collections of values to produce a single or collections of results, exactly like in the equations I sent you. Okay. Here is an example. Our collections are all polyhedral sets. Okay. So here is some variable f that is defined over this pyramid. It's a tetrahedron. And there is an answer y that is produced, and it happens to be one-dimensional. Okay. Are you seeing the pictures? Are you able to distinguish that one triangle is purple and the other is blue? And I apologize because I was told much later that sometimes if someone is colorblind, that distinction is not very clear. So if that happens, I'm sorry about that. Okay. All right. What I am doing is I am combining all the points, all the values of f in this triangular slice. I'm combining it by some operator like max or like addition to produce a single answer. Okay. So here is a simple example. I write a program for I equals 1 to n. I compute j as, if you can see, the ith value of y is the sum of xj from j equals 0 to I. Is that clear? Can you read this program and see that that's what's happening? Okay. How many of you think that this is a stupid program? How many of you think that this is not stupid? What is the complexity of this program? I equals 1 to n, j equals 1 to I. What is the iteration space? Or 0 to n, 0 to I. What is the iteration space of this program?
It's a triangle.
It is a triangle, right? So what is the complexity of this program asymptotically? Order n squared,
And square, yeah.
right? Can you think of a way to execute this program in a way faster than n squared in linear time? I have an array
Instead of
f. Yeah, go ahead, go ahead.
instead of calculating every time the summation of all xj's, we can just take the previous element of yi and
Absolutely.
add the
That is,
x.
that is simplifying reduction. So you are going to compute an array given by this equation, okay? And the program on the left is the silly and most direct way to implement this equation. But of course, as you said, I have to initialize the first value of y to x0, and then that's it, right? So this is a transformation that takes a, I haven't showed you what the transformation is. It takes a quadratic time program and gives you a linear time program. Okay? The exercise problem that I gave you is asking you to do exactly this kind of analysis for something that is not as trivially simple as this one. Okay? This one is trivially simple, but I want to now show you how we do that. Okay? So a little bit of history. Like I said, in 2006, we wrote a paper that showed, that presented this theory of simplifying reductions. And then 15 years later, January of this year, what the main thing that these authors did was that they said that they showed that there are many examples in probabilistic programming and Bayesian learning that actually are instances of simplifying reductions. But they also found that the problem that they had to solve was a little bit more general. The reductions that they had, the equations that they had, were not one single equation like we handled 15 years ago. There were dependencies amongst the variables, amongst the results, and so they had to simultaneously solve the scheduling problem and the simplification problem. And they gave a brute force solution, which is in the form of a bilinear programming. And what I was able to do around the same time was to have a significantly simpler algorithm, which was just the classic scheduling kind of problem. So I'm going to return to my example, which is slightly more complicated than the most trivial one. Okay. If you look at the code, okay, I have this triply nested loop. It is computing every answer yi by visiting all the points in the JK triangle. You see that? K equals 1 to I minus j, or j equals 1 to I minus 1. Okay? And then for any given value of j, the k goes from 1 to I minus j. Okay? So there is a triangle. The size of the triangle is changing because the upper bound is related to I. Okay? Or the upper bound of the two inner loops is I minus 1 and I minus j. Okay? And then I am computing this yi is accumulating f of ijk. So I can describe this as a code, I can describe this as a picture, and I can describe this as an equation. Which description do you think is the easiest for you to follow? What is your preference? Are pictures useful? So at least for me, pictures are useful. So I'm going to continue to use pictures rather than these equations. Okay. I will show you the equation or I'll show you the code, but really the picture is worth 1,000 words. So the first point to observe is that if at ijk, at every point in the domain, the value of f is the same, okay, then all these order n cube input values have to be read and there is no hope of simplification. Okay? The simplification is only possible if there is some sort of a reuse among the different values of f. Okay? I'm going to give you the simple case of reuse. Look at the body. Instead of fijk, it is x sub k. Okay? Now here, I would like you to think back. I have a loop body, okay? And I'm basically saying read f of k, x of k. So the right-hand side of this read statement over here, sorry, I shouldn't click on a display PowerPoint, right? The right-hand side of that assignment statement, f comma of I comma j comma k, is replaced by xk. Okay, I am reading a one-dimensional variable x by an affine function or a linear function. That linear function maps ijk to k. Okay, what is the shape of the matrix? It's 1 by 3 because x is one-dimensional, the loop body is three-dimensional, the data space is one-dimensional, the iteration space is three-dimensional. So I'm going to map a three-dimensional point to a one-dimensional point, right? So the read function is given by a matrix that is 1 by 3 and its value is 0, 0, 1. Okay? It is mapping three-dimensional space to one-dimensional space and it is a linear function. It must be many to one. Many points in the iteration space read the same value of x. Right? And the compiler can very easily do the analysis. If you compute the null space of this read matrix, null space of the kernel, it is spanned by two vectors 1, 0, 0 and 0, 1, 0. The ij plane, all points on the ij plane read the same value. In other words, a compiler can very easily identify that everything on the green plane in this picture has actually the same value. Okay? So now what I'm doing is the following. I am accumulating all the purple slice and the blue slice. Okay? But many of the values in the blue slice are identical to the values of points in the purple slice. And just like you made that previous observation, instead of accumulating all of those points, why not use the previous result to compute the next answer? Okay? So the intuition is exactly the same. And I'm going to describe to you how the simplifying reduction transformation works. Okay? What do? You take the purple triangle and you translate it along some vector in the green plane, along the reuse. Okay? So in this case, I chose 1, 1, 0. When I do that, a large number of points in the blue triangle are covered by, have the same value as the purple triangle. Okay, so I don't need to accumulate everything in the blue triangle. I only need to take the previous purple result and accumulate all the points on that blue line at the bottom. That's all I need to do. Okay? Another way of thinking about this is I have to do this for all the slices, right? For every result that is computed. In other words, I'm going to take that entire pyramid and translate it in the direction of this green vector. And what happens is everything that is in the intersection of the two, I can get rid of. Okay, so instead of doing this computation on all this three-dimensional domain, I am left with a residual computation that is only on the facets of this domain. In this case, or some subset of the facets of this domain. Okay? So I am left with a residual computation that is only on the bottom plane over here. So I have gone from cubic to quadratic. Okay? Next question. Is there further reuse that I can do? And yes, indeed. Remember, my green plane was the reuse space, right? I chose, there is a cubic to linear, 3D to 1D reuse. So even on the bottom plane, some points actually have the same value. If I go along the 1, 0, 0 direction, remember, the value that is computed, the value of f is the same. So I can also exploit this reuse, and I find that the blue answer, it can be computed simply by taking the red previous answer and doing one extra computation. Okay? So these geometric transformations, the identification of the reuse space, the identification of the reuse, the faces of the polyhedron to exploit, etc. That is the algorithm for simplifying reductions. And in fact, this example, if you work it out, you will see that it is the prefix sum of a prefix sum of the input x. Okay?